So we have a complex function f of z, okay? And it's a function, what's a complex variable? So we need to know how to represent a complex variable first, right? So the complex variable is, one or two ways of representing a complex variable z. We'll use what's called as Argand diagram. I mean, that's the typical way to denote a complex variable. So it could have a real part, of course, and an imaginary part itself. So in the Cartesian kind of coordinate system, I would write it as x plus iy. But in general, I can write it as, let's say, this is a complex variable, z, which has got some real part and the imaginary part. But I can write it as, this is how we'll be representing all the time, okay? We can represent the same complex variable, which has got a real part, imaginary part, as r exponential of I theta, where r is nothing but x squared plus y squared, or it is equivalent to the modulus of the complex variable 2, right? If you just write as r cosine theta plus I sine theta, that is modulus is z times z star is z squared, gives you r squared, right? So r is nothing but modulus of z, okay, which is nothing but z times z squared, square root of that. And if you, or you can think of as 2, okay? So both are the definition of r here, and theta goes from 0 to 2 pi. The directions and everything will become important. We'll talk about all these things. So this is complex variable itself, right? And your complex function, which can be which will also have its own real part and imaginary part. What is the difference? You've come across real function, real variables, and all that. The main difference between a complex function and real function is a complex function at a given point in a domain, it could be single valued or multiple valued, can have many values. So that is the main thing that we always will be talking about. So a complex function can be single valued, that is, it has unique one value at a point, or multi-valued. What do you mean by that? Let's try to understand this for a minute. Suppose my function, complex function, f of z is square root of z, where z is a complex variable. Okay? Since I can write z like this, so this is nothing but r to the power half exponential of I theta over 2, right? If I use the complex variable as this. Okay. Fine. Now this variable, supposing I have a closed contour and I go around a contour around z equal to 0. Here it has a value what? R to the power half, right? Theta equal to 0. When I go around once, the same point, it has a value r to the power half exponential I pi. So it has a value negative r square root of r. So it develops two different values. But if I go around this z equal to 0 point 2 times, that is theta has become now 4 pi, I recover my original value. Okay. So this square root any if z is a complex variable, anything, any exponent, okay, of this type, 1 over any radical like this will be a complex function, will be a multi-valued function. It's not a single valued function. Z to the power 1/3, 1/4, 1/5, all of them will be automatically a multi-valued function. Okay, so this is the main difference when you talk about real variables and a real function, complex function. A complex function in a given domain in the Argand diagram there, which represents a complex variable, can be single valued or multi-valued function. So many of the theorems that we'll be studying, we will, even though a function may be multi-valued or something, will be distorting the contour and making it such that it is single valued, at least in the distorted contour or whatever it is. Okay. So one way is that we know that this is something that you will see later on, you'll understand it later on, at this point maybe a little bit. So because for z of half, what we will do is, we'll not go through this, we'll not cross, we'll put a barrier and try to go around and never cross basically z equal to 0 point. But what I'll do is, as though you could think of what is it called, what is the manifold that the paper that you do, what is it, I forget, torus. I mean, it is.
Oh, you're talking about like the Mobius strip?
Yes, Mobius strip. Okay, so it is not. Think of it that way. Okay, I mean they're continuous, but it is not a real, a loop like that. Okay, like that. You can obviously think of all the display on the second floor of the math department. Yes, like a Mobius strip. Exactly. Yeah. So you think of it like that, and then I have unique values. It's only if I cross that point I'm having trouble. So I will try to distort the curve so that I never cross the x-axis, real axis, and I'm introducing some kind of barrier which is called branch cuts, and z equal to 0 will be called as branch point. So all these definitions will become important a little bit later, but all I'm trying to do today is that a complex function can be single valued or many valued function. So this is called as branch cut. We will introduce branch cut so that we are using a contour where it has unique value all along. Okay, I mean it is single valued everywhere on this path, in this distorted path that I have created. Okay, so that is
in 0 to 2 pi.
Huh? Yeah, here it is 0 to.
It's in a fixed interval.
What?
You are not again rotating.
I'm not again rotating here. Yeah. I'm not again rotating. I'm just the way you want to cut the strip and join it. It's like that. It's a closed contour, because all my theorems will also be closed for closed contours. Okay, so I mean this one will become clearer once we do more thing. But for the moment, just understand it can be single valued or multi-valued. See, in this case, like let's look at, so this one, square root of z is a double valued function. So multi-valuedness of a function depends on how many times you have to go around the branch point before you recover your original value. That's the multi-valuedness. Okay. So in this case, square root of z, you have to go around z equal to 0 2 times. When theta equal to 2 pi, it has two different values. When theta becomes 4 pi, you get back the original value. So at least 2 times you have to go. So that's what the multi-values. Of course, it has also got two values in this case, z to the power of half and minus half. Right. So it develops two values, theta equal to 0. That is when you, or maybe you can say 0 less than theta less than 2 pi. In this regime, you have one value, right? And you have a value of this when you go from 2 pi less than theta less than 4 pi. That is, it has, and then it will get back to its original value after that. Okay, so all right. Natural log of z. Okay, z is a complex variable. All right. So if I have to write this, what? It is natural log of r exponential of I theta, right? I mean, which in the principal plane, I can write it as natural log of r plus I theta. So principal plane is 0 less than or equal to theta, theta less than 2 pi. Now, when you go around second time, what happens? What happened to, if I go theta becomes theta plus 2 pi, right? I mean, we have to increase that by that. So this will become natural log of r. In this, theta will become theta plus 2 pi. Wherever it is, it's not just that point in general, right? It will have theta plus 2 pi. So I have this. So every time you go around, I get a different value, plus I theta, 4 pi, right? I mean, and so on and so forth. I mean, I'm not getting, so I will never get this, okay? I mean, 4 pi less than whatever it is, the next theta. Okay. So I mean, after n, it is 2n pi if you want to write it. I mean, it'll keep on changing and never get the original value that I have. So natural log of z is a infinitely many valued function. Okay, so that is the extreme case. Every time you go around this z equal to 0, you're going to get different values when you cross the real axis. Okay. So these are the two extreme cases, just for you to understand, why this word is very important. The Cauchy theorem that we are going to talk about applies when the function is single valued. Okay, in a given domain, it has a single value. So that's what we are going to first talk about. Okay. All right. For the moment, it is just enough to know that a complex function can be single valued or multi-valued. If it was just z, of course, there's no problem. Z squared, no problem. Z is a complex variable, and let us say it was a function like z squared. That is not a problem. Okay, that will be single valued. Okay, so, all right. Okay, the first theorem, or whatever we want to call it, that we want to discuss is the following. Okay. A function is analytic inside the domain and on a contour. Okay, I mean, single valued and analytic. Okay? Single valued you already know. Single valued is the function has unique value at every point of the domain. Analytic, we have come across this word before. What it means is the function has its derivative, right? First derivative. But what we want to show is that if a function is analytic for a complex function, is single valued, for a complex function to be analytic, the first derivative also had to be unique. Okay, so let me write down. This is what leads to Cauchy-Riemann condition. A complex function for a complex function f of z to be analytic, this is sort of the new thing, right? I mean, for real variable, real functions, we know analytic means its derivative must exist. That part of it you already know. We have come across this before. I mean, that's how you can write the Taylor's expansion, all that stuff, right? Okay. This is other word. This derivative, that f prime z that you take, must be unique. Let's try to understand, okay? So f of z is a complex function with the real part. I'll do an example, then you'll understand more, but let's just, it's got a real part, which is u. V is the imaginary part of the function, where z is nothing but x plus iy, or you can think of as r exponential i theta. Okay. That z is that. Why is it here z and xy? Because z can be written x. This is nothing but real part and imaginary part is there also. Okay, it's a function of x and y. All right. F prime is nothing but, we know from real variables what is f prime. We can write that and then we come to it. This limit L is nothing but f prime z. We can write for the real variable. This is how I will put it. If f was z was a real variable, okay. This is the definition of the first derivative that we all know. Okay. The only difference now is delta z is what? Delta z has a real part and an imaginary part, right? Here. So this is my Argand diagram. Real part of z, imaginary part of z. So I can approach delta z tending to 0 either in two ways. I can set delta x, let's say delta y tending to 0, and I can set delta x identically equal to 0. So I can do two ways. This limit I can approach two ways. Is delta x tending to 0 and delta y I put as identically equal to 0. Alright, so the limit can be, I can approach it. The first case is delta y tending to 0, that means I'm approaching along the imaginary axis. The second case is, the other one is 0, so I'm approaching along the real axis. Okay, so this is approaching along the real axis. This limit is taken like that, approaching along the imaginary axis.
We are solving in two dimensions.
Huh?
Means z is a function. Z contains both x and y. That's why we consider both the limits.
Right. I mean, yes. Delta z is that. Delta z is delta x plus delta
We need
I
to
delta
consider
y.
both the limits.
Yeah, both. We can approach the limit either way. If you have to get the limit, that's it. So if I do that, what we should have is the two limits. How we approach should not matter. If they're identical, then f of z is analytic. In some cases, you may cook up a complex function. It may not satisfy this condition. Okay, so then that complex function is not analytic. So this is a condition to check the analyticity of a complex function, that the limit, for the first derivative, how you take, whether you approach along this or along that, must be identical. If it is identical, then that f of z has unique first derivative. Okay. So in this case, f of z will have unique first derivative. So this leads to what is called as Cauchy. I'll prove it for you. This is what leads to Cauchy-Riemann condition, which gives you obviously we are taking the first derivative. That means partial derivatives, all partial derivatives should exist. Partial u with respect to x, partial u with respect to y, partial v with respect to x, partial v with respect to y. They must exist, and in addition to that, it must satisfy the following condition. Partial u with respect to x, that is the real part of the function with respect to x, must be partial v with respect to y, and then partial u with respect to y must be negative of partial v with respect to x. Both these conditions have to be satisfied. It's not sufficient you check one condition. No, both these conditions have to be satisfied for f of z to be analytic. Let's now understand this, unpack this, where that is coming from. All right, so let's take first limit L1 is, let's say limit, I'm going to take this, right? Delta x equal to 0, delta y tending to 0, let us say. This is what? U of x plus delta x. that plus I B I think this. All right, minus u x y minus I v x y divided by delta x plus I delta y. This is the meaning of this statement, right? I mean, all we have done is f of z is ux plus I v y from the definition, and since it is z plus delta z, I have to write in this way. Now delta x equal to 0, the case 1, no. Now I want to do this as case 1, let's first do that. Yeah, let me call this as case 1, case 2, it doesn't matter, but I just, okay, let me put this delta x tending to 0 and delta y equal to 0. If it's delta y equal to 0, this is 0, right? So what I have is, this limit is nothing but u of x plus delta x comma y. Okay, this is delta y is 0, and I'm going to call this minus x comma y. That is one of the terms I have, plus I b of x plus delta x comma y minus b x y divided by delta x, right? This is my first limit. Let me just, yeah, I have not, yeah, here I put already delta y equal to 0. I put delta y equal to 0 here. I think I already have put it here. Okay, so this is my limit when delta x is tending to 0 and delta y identically equal to 0. So I'm approaching along the real axis in this case. Now what is this term?
F of u.
Partially with respect to x, right? We are changing x and keeping y. So this is nothing but, my first limit is nothing but partial of u with respect to x plus I, and this term is partial v with respect to x. Okay, that is L1. What about L2? If I did the other way around, L2 is, the other limit is delta x equal to 0 and delta y tending to 0. What do I get? So delta x equal to 0, so I'm putting this,
Delta u by delta
and this
y.
is 0, right? And here I have I delta y. Okay, so I will have L2 is nothing but u x y plus delta y minus u x y, okay, divided by I delta y, right, plus I v of x comma,
Y plus.
get rid of all these things. Plus u. There is IV x comma y plus delta y minus v of xy divided by I delta y. Okay. So this limit, in the limit delta y tending to 0, this is nothing but partial u with respect to y with the negative sign because I is in the denominator, right? minus I partial u with respect to y. Okay, and that I and I will cancel here, and nothing but partial v with respect to y. My y and v look the same. I'm going to put it like this so that you know this is v. Okay. So what we are saying is, if f of z is unique, these derivatives L1 and L2 must be identical. So we have to compare, that means the real part of L1 with the real part of L2. So for the derivative for f of z to be analytic, the first derivative must not depend how you approach delta z. Okay. Okay. So that leads to this condition. So this is your real part, and this is your real part. So we have partial u with respect to x is nothing but partial v with respect to y, and partial v with respect to x. Comparing the imaginary part, we'll have partial v with respect to y is that? Is equal to partial v with respect, partial u with respect to y is negative partial v with respect to x. Okay, the imaginary part here is this, right? And here I have partial u with respect to y with a negative sign. Okay, so both these conditions have to be satisfied, and this is what is called as Cauchy-Riemann conditions. So this is first of the theorems of the analyticity of a complex function that you have to do, where u is nothing but the real part of, this is what you have to understand what is u. U is the real part of your complex function, and v is the imaginary part of the complex function. So this corresponds to that, whatever it is, okay? And so let's do an example so you understand what it is. Okay, I got two complex functions written there. Is this clear what I've written? Is there any questions here? It's fine? Okay, just we are comparing the real part with real part, imaginary part with the imaginary part. That's what gave you those conditions. Okay. All right. So I got two complex functions here. tell me which one is analytic and which is not analytic. First one is analytic, yeah. So, and this one is what? uxy, the real part of the function is x squared minus y squared, right? The imaginary part of the function is 2 times xy in this case. Here, the real part of the function is 2y. The imaginary part of the function is simply x, okay? So let's come first. Yeah. Okay. That one. The first one, clearly partial u with respect to x is 2x. Okay. And partial v with respect to y is 2x. So this first condition is satisfied definitely. And similarly, partial u with respect to y would be negative 2y, and partial v with respect to y is 2. What is it? Partial v with respect to x. Actually, second condition is actually partial u with respect to y and partial v with respect to x. Right? I mean, is 2y. So this has to be opposite sign, right? Partial u with respect to y should be negative of partial v with respect to x. So this condition is also satisfied because they have opposite signs. Whereas here it does, one of the conditions will be satisfied but not the other one. So partial u with respect to x is 0, and partial v with respect to y is 0. So the first condition is satisfied, but the second condition is not. Partial u with respect to y, partial v with respect to y is 2, partial v with respect to x is 1. Of course, 2 is not equal to minus 1. Okay. So this condition is violated, so this complex function will not be analytic. You can, if you don't remember the Cauchy-Riemann condition, you have to go back to the original definition, which is easier for to do something, because something like that is more complicated, because you have to look at that limit. If you don't remember it, you have to go back to the drawing board and then start doing that, right? I mean, read what is the real part and all these things. You have to start doing it because that's how this expression is for more complicated complex function. Okay, this one you can easily do. Whereas here it's going to be x plus delta x whole square. You got big so many terms, right? It's not easy to do it. Okay, so yes. So this is what we mean by real. So you have to know u is the real part of the complex function. That is what you have to remember. V is the imaginary part of the complex function. Okay. All right. Okay, let's talk about the first of the theorems. Now that you know what analytic function, complex analytic function is, right? That is, its derivative exists and it should be unique also, and it has to satisfy Cauchy-Riemann condition. So, if for a complex, for an analytic function, okay, so what this theorem says is the following. We have some domain. Now f of z is analytic in this domain. Okay, both inside and on the contour. Okay, we just introduced the definition of what f of z is analytic. The first derivative should exist. All the partial derivatives of the real part and imaginary part of f of z must exist. Cauchy-Riemann condition must be satisfied. Then, and there are no singularities in this domain. Okay, so f of z is not blowing up anywhere. It doesn't have a branch point. It doesn't have singularity. Okay, then closed. This loop means we are doing a closed path. Okay. So contour integral of an analytic function, of a complex analytic function, must be 0. Okay. So where does it come from? All is coming from whatever we have proved. Okay. So let us examine closed contour of f of z dz. Okay. All I know is it's a complex function. So I can write it as like this. And dz is nothing but, I can write it like this. Okay? Nothing, I've just used this. Okay. And I have ux, y, dx. I have minus exy, dy. Okay, that's one term. Plus, I'm under closed contour, which is I times vxy dx plus uxy dy. All I've done is expanded it out. So ux dx, this one is minus v dy, and this term is uxy, is it what it is? Vxy, I times, I've taken out ixy dy is there, ivxy dx is there. Okay.
There's the I missing.
I is here. I is common to both of them.
Okay.
Okay. So I have put all the real part here, imaginary part separately. Okay. Now, the only other thing that I know is this is analytic, so I must have this condition also satisfied. Partial u with respect to x equal partial v with respect to y. Partial u with respect to y must be negative partial v with respect to x. Right? This is your Cauchy-Riemann condition. Because f of z is analytic, this has to be satisfied. Now, I have a contour integral and I know this. Does anybody remember how to convert a contour integral into a surface integral? One of the vector calculus theorems that you might have come across. Line integral that you convert into surface integral. At least the name of the theorem, let us say.
Am I thinking of Stokes' theorem?
It is like it's a green, So one is convert into volume integral, line integral to surface integral. It's one of the divergence theorem. Okay, yes.
Divergence theorem.
We can say divergence theorem in 2 dimension, or it's also called Green's theorem. Okay, it is. Yeah. So that is what we have to do to convert that. So let me just. I'm pretty sure nobody remembers this theorem. Let me go back and view refresh that. Okay. So I'm going to convert this, basically both these integral into a surface integral. Okay, so double integral, that's what I'm going, you are. So I'm going to convert that into surface integral. That will give me some partial derivatives, okay, which I can connect to that. Both of them, I need to convert the line integral or contour integral into surface integral. Okay, so what it is we have to use what is called as Green's theorem. Green's theorem, or we call it as divergence theorem in 2 dimensions. Strictly the theorem writing, okay, but so what it says is, if this is true, then contour integral of such a function which is continuous, p is a continuous and well behaved this we came across in real variables, but it is not applicable here, is nothing but partial q with respect to x minus partial p with respect to y dx dy. Okay. So all it says is p and q are continuous function, and don't worry about the simply connected region. What it says means is a region where the contour can be shrunk continuously to a point. Okay, so such a thing is called simply connected, rather than doubly connected regions where it cannot be shrunk continuously. So you have a simple contour. The function here p and q are continuous in this domain and on the contour, and the curve can be continuously shrunk to a point. That's all we mean by simply connected region. Then line integral of p dx plus q dy is nothing but equal to this. We convert that into surface integral. It's a double integral now. We're going from single integral to a double integral. Now, I mean, it looks complicated, but then it's easy actually. So what is my pp dx, right? So this is p in this. P is u here. Q is negative v here, right? I mean, in this p dx, p is really v here. Q is plus u here, right? So this integral, the first integral, so basically contour integral of f of z dz becomes what? Double integral of partial q with respect to x. So that's partial v with respect to x, that is the first term, minus partial p, which is partial of u with respect to y. That is my first term, dx dy. Okay, so this is my first, this contour integral has become this, plus I v dx. So v is so v is p. So q is u. So partial of u with respect to x minus partial of v with respect to y. Okay. Dx dy, and I have this double integral now of this quantity. So this line integral, I have I, okay. So this line integral became that, and this line integral became that double integral. And we know from Cauchy's residue theorem, if f of z is analytic, partial u x with respect to x should be equal to partial v with respect to y. So this becomes 0, and we should have what? Partial u with respect to y plus partial v with respect to x should be 0. So you can pull the negative sign, so this is equal to 0 also. So what we have is okay. So if f of z is analytic in a domain, then I must have this condition satisfied. Partial c contour integral of such a function must be 0. Alright? Alright. So this is what we'll have to extend for the, if the function is not, that's what is going to lead to Cauchy residue theorem eventually. If it's not, what happens, what we have to do, right? All right, now this has got some immediately a few corollaries. They're very simple to understand. I think I'll do that, and today we'll stop here, and then we will, we have to go through several more theorems. I mean, what happens for real variables, Taylor's series, right? Does it apply for real function? Does it apply for complex function? And if it does, it's not the case, what kind of series can we apply? That's what leads to something called Lorentz series. And one of the terms of the Lorentz series is what is the residue, and this is what leads to Cauchy residue theorem. So we're trying to sort of develop analogy between whatever you know for real functions with complex function, right? So even for derivatives, we know, I mean, okay, derivatives means limit, you know, how you take the limit is important. You take the first derivative, and if the two limits are the same, then it is analytic. Okay, the simple one of the thing is the following. A function is a closed loop. It doesn't have to be a perfect circle. What it means is closed contour, okay? It can be, it doesn't have to be that, okay? That's why you can do all these distorted contours. As long as closed, it's a closed contour. So I have a closed contour where f of z is analytic. So I go from A to B, and then I come to B to A, okay? So my closed path is these two contours, C1 and C2. So Cauchy's theorem says if f of z is analytic, whether you go along C1, which is A to B, let's call it A to B, along C1, plus B to A along C2, this should be 0, right? But it's a closed path. So what does that imply? That says the integral along the contour, whether you go A to B f of z dz, can take you to the negative side, along, whether you did the contour along A or along C2 does not matter, it's exactly identical. It only depends on the endpoints.
After dz is there a bracket?
What did you say? What bracket?
The notation, I didn't get this.
Which notation? Here?
The f of z.
F of z dz
Okay.
along C1. Okay, I'm just saying along this path. I'm just taking this it was a full contour integral, right? I mean, this says, this is my theorem. Closed contour. My closed contour C includes two parts, C1 and C2, right? I mean, okay. So what it really says is, it only depends on the endpoints A and B. Whether I go along this, now it is C2 along the same direction, okay? A to B, okay? This is the closed path for you. And since I'll take it to the other side, this is negative, so they are in the same direction. So your traverse in this integral along the same direction is the same. That's all it says. Okay, me now. So that is first theorem. The other theorem is the following, which is the more important one. F of z is, I'm going to call it corollary when they fall from. F of z is now f of z is analytic in the inside and on all these contours. Okay, so I'm going to call A, B, travel counterclockwise. All these directions will become important too later on. Okay, let me call this as gamma, small circle, C as big circle. Let me call this CD. So I have a small slit in this contour, this slit with this small, and let's say this is really centered around the center of the circle. Okay, it doesn't look like that, but it doesn't matter. All right. So Fz is analytic in the region on C and on gamma, everywhere. Okay, in this interior region and on all the contours. So if I have to apply Cauchy's theorem what does it say? How will the Cauchy theorem look like for this distorted contour?
Should there be a minus sign for the one in the...
Here? Yeah, there is a minus here, but I changed the limit. That's what this is important. There is a minus sign here. So this is what I meant by saying you're traversing in the same, this is the path for closed curve. The value of the integral a to b along C1, it doesn't matter, if it was like distorted, it is the same thing. All it matters is end point. So it doesn't matter whether the C2 was like that or, so all it matters is the end point. It's a closed contour. So the size of the width of this doesn't matter at all. Okay, that's what the meaning is. So it is in the same direction, A to B, they are both in the same direction. So the limits are the same also. Okay, the negative sign was there, but I have absorbed it and I've changed it. Okay, this is my contour now, and f of z is analytic. So what should the theorem, if I have to apply that theorem, C is closed contour. The meaning of C means closed contour.
E to B, then minus C to D.
Okay, A to B, okay, fine.
And then the regions contour
FZ DZ,
B to C.
okay, and then you're coming from C to D, right? In the opposite direction, okay? And then,
Then minus C to D. Then C to D minus.
yeah, that's only part, this only, you can traversed here and traversed here.
B to C also.
What is B to C? No, this, okay, so we are calling this whole circle as a big, if you want to call it gamma 1, okay, so that you know it's not a C, okay, let's call it gamma 2, the small circle is gamma 2. So we also, then we have on gamma 1 f of z, okay, that's a bigger circle, right, plus smaller circle
Yeah.
in the opposite direction, but that we can put the direction also if you want, okay, equal to 0. This is what the meaning of this C is, closed contour, right? Here C to D is fine, but here we have to put the direction which is counterclockwise, and this is clockwise, right? This is counterclockwise, and this is clockwise, right? This is going clockwise. Gamma 2 is clockwise. Now, if this slit was really small, then they are going the opposite direction, then we can say
Cancel it.
they will cancel, okay? The contribution of the integral along A to B, C, D will see. But so what we have is, this now becomes, what it says is value of this contour integral, whether you calculate it on gamma 1, the bigger circle, now because of the negative sign, is same as value of this closed integral on gamma 2, because of this clockwise negative sign is become now in the same direction. Okay, so I'm just going to say if it's clockwise, anti-clockwise. So it doesn't matter that the value of the integral that you if it's analytic, whether you calculate on the bigger circle is identical to the value of the integral calculate on the smaller circle, as long as the function is analytic in the interior region and on the contour. Okay, so this is, we will exploit all these things. Okay, so these theorems are important because this is the Cauchy-Rosati theorem that we will prove will hinge on this particular theorem. Okay, whether I calculate on outside or inside, because I'll eliminate. Let us say the function blew up here, okay? I eliminate that region, and in the intermediate region it is analytic, and I'll exploit that kind of property and calculate the contour integral on a bigger circle by just calculating the contour integral on a smaller circle, okay? So in this sense, this is an important theorem, corollary following from the Cauchy's theorem, because the Cauchy-Rosati theorem will hinge on this particular aspect of the thing. Okay, so what we have done today is just if the function is analytic. That's all we have done. We'll just relax that condition. Basically, if it is not analytic, how to do it, because that's the most interesting one, because our whole goal is to calculate integrals, not something which is zero, right? I mean, so that's what we will do. The whole idea is how to choose the contour will become important. What type of contour is closed contour, then we have to decide what type of contour should I choose. Okay, and so those are the things which will come slowly. We'll develop that to solve. Basically, we want to calculate infinite integrals, right, along the real axis or along the imaginary axis or whatever it is. From a closed contour, we have to sort of get, that is what our goal is, okay. So up to this point, is any questions, or it's clear? Okay, so the concepts are fairly simple here, and most of it will follow some of these diagrams basically, and so you'll see you'll be able to calculate integrals very quickly. Once you understand the theorem, it is fairly simple, and all you have to learn is how to calculate residues of different types of functions. And if a function is not single valued, multi-valued, what type of curves contours I'm going to draw. Okay, so those are the aspects that we have to learn.